Hold on. Then I'll do your introduction.
You
Give
don't
me a second. Let me pull up your C. Okay. Let me introduce Bhaskar. So Professor Bhaskar Choubey has received the DPhil degree from the University of Oxford as a Rhodes Scholar and BTech degree from REC Warangal. He is currently the chair of analog circuits and image sensors with Siegen University. In the past, he has served with the University of Glasgow, Somerville College, and the University of Oxford. Professor Choubey has received the IEEE Sensors Council Gold Early Career Achievement Award and Merrill B. Reed Best Paper Award from the IEEE Midwest Symposium of Circuit and Systems. He is currently the chair of IEEE EPPC Working Group on ICT in Europe. He is an associate editor of the IEEE Sensors Journal. Bhaskar, over to you.
Thank you, Alex, for the kind introduction. Good afternoon to one and all. From yesterday, we have been having a number of lectures on designing neural networks. So to give you a bit of relief, I'm not going to talk about neural networks. We are going to change a little bit topic, and we're going to talk about sensors. The rationale will become very clear as to why a sensors person is talking to potential future neural network developers. But let me start by raising the question of what is the aim of engineering? I mean, in general, we are aiming to produce something, overall speaking, and that production requires measurement of the knowns, and this could be your product, and the product could be in terms of volume, quality, its physical properties. You might be measuring the climate, whether you can make the product or not. You could also be measuring the market, so you could be going beyond just measurement of environment. So overall, there's the sensory activity. You are sensing things. This could be your product, product-related environment, or product-unrelated environment. The second thing one has to do is forecast the unknowns. And this could be production factors, what kind of market you are getting, the raw goods, the liquidity, once again, production of climate, production of what maintenance would be required to your manufacturing tool. So these activities would come under what I would call as the inference or security, or securing the production line of your management. Now, for the last 2 days, we have been talking quite a lot about inference. We have data. How do we extract meaningful information out of this data? And that is a key problem. And that problem has quite a lot been influenced by the way our computation has grown. And the next 3 or 4 slides, I'm sure by now you guys have been bored to hell of seeing those slides, but they're important. They're important in the sense is that is our classical computer. We have the von Neumann architecture. There's an input. The input feeds data to central processing unit, which in turn talks to memory, and then the CPU gives data to the output unit, whichever that output unit be. Now, courtesy microelectronics, all of these have been made quite cheap. The computer is cheap. Most input functionality has become cheap. Output has got down the cost. So we can make very powerful computing machines. These computing machines do not learn by now, we know, which means they do not solve unpredicted problems, or they do not interpret new data. So unfamiliar problems are not to be solved by them. You would also know this thing which has been happening for a long time, which is that the processor ability has kept on increasing. The same has not happened to the memory. So we have this old problem of computer architecture called processor memory performance gap, or the bottleneck. So one aspect, and because the way processors and memory or input output talk to one another in a computer are through various system buses. You'll have the control bus, address bus, data bus, or 2 data buses, depending upon which architecture you use. So in essence, all the data has to move between these based on how fast the system bus is going to be, how fast the interface is going to be. So this was a well-known problem, and there has been, and this is where some of the new architectures, for example, neural networks or AI-related architectures, are helping reduce this or circumvent this processor memory performance gap or the memory bottleneck completely. We also know this thing, AI systems are, they're solving this bottleneck. They're also good for learning, solving new problems. However, the majority of implementations of these learning algorithms are on non-learning hardware. I mean, the famous Google Brain project. I mean, earlier Harish was talking about the AlphaGo challenge. If you looked at the Google Brain project, which were able to identify a cat in YouTube videos, it still took 16,000 processors, 100 kilowatts of power. Essentially speaking, that because of the sheer volume of processing ability required, generally these things are in data centers or high-powered GPUs. Now, why am I talking about these things when I'm going to talk about sensors? Because what has happened in parallel is microelectronics has also given birth to low-cost, versatile sensors. All of you would have tons of phones on your mobile phones. So there would be cameras, there would be gyroscopes, there would be audio instruments. And because of this low-cost sensors, we are producing a huge amount of data. Look at a traffic camera, it produces a terabyte of data a day, which is difficult to process, if not impossible, certainly not to do in real time. So it leads to the big data problem. As to one part of the problem is how do we transmit all of this data and receive the data at the other end? And then how do we process it? Now, the classical sensing modality, now we are talking about data till now, but where does the data come from? It comes from some sensor. I mean, either it could be a human sensor inputting the data, or it could be a physical sensor which is collecting the data. The classical approach to sensors has been this. There is a sensor which measures a physical quantity. We have some form of signal conditioning after that, generally speaking, an amplifier, because sensory data is quite weak. Say, for example, if you're measuring the electrocardiogram, the signal is quite weak, you need to amplify it, or the signal might be in a different domain. So you might have a sensor which is giving 50-volt data, and then you want to transform it back to 3-volt data to transfer. So we do some form of signal conditioning. This is followed by an analog to digital converter, which converts the data to digital because digital is good for processing. And then we do processing. Processing could be one of many types. It could be direct display to an end customer. It could be storage in a memory. It could be transmission to a central center. And then further processing. It could be stored and processed on and on further. The trend which has been is that sensors are cheap, so are the electronic components. So collect as much data as possible and analyze later. And the analyze later comes where we hope and we pray. We hope that we will have the ability to analyze this huge amount of data, and then pray that out of this huge amount of data, we will have some meaningful information which will come out. And this is something which you need to understand clearly, the differentiation between data and information. So sensors produce, most of the sensors we have are producing data. They're not producing information. They're just taking a picture. They're not taking it's your picture in front of Hampi ruins or in front of Taj Mahal. Now, this means that one domain architecture is not there just for processing. It's also there for all sensory applications. So in a sense, we have a system where there are sensors which are producing huge amount of data. And I have drawn sensors as much bigger as than standard input of a computer, because there's a diverse variety of sensors and a diverse amount of data they produce. So all of these sensors then have to talk to a central processing unit, which in turn has to talk to a memory. And CPUs then also have to talk to the output, which are generally actuators. I mean, if you're having a machinery system, you're recording a data, you want to do something with that data. So you might have some actuators as output. And we have those bottlenecks again. We have the bottleneck of communicating between sensors and CPU. We have the bottleneck between the processing unit and actuators. So what we used to have the memory processor bottleneck, now we have the sensor processor, sensor memory, and processor actuator processor memory bottleneck. So if we continue this line, wherein we keep on making cheap sensors, I keep on producing megapixel images, hundreds of megapixel, and somebody else keeps on making good processors, we will keep on going down this route, wherein we would have more and more bottleneck coming here. And we will do one of these two things. Either we won't care, we will just be collecting a huge amount of data and do nothing with that data, which most of us are already doing. We're taking pictures and doing nothing of the pictures. Or we will be taking bad inferences out of it. We will not get all the information which is available in those data. Now, sensors are huge, and this is why the problem lies. There is no one sensor to talk about. We might be measuring any and all physical properties, right from acoustic, sound, vibration, chemical. Optical sensors themselves are of n number types. We have got sensors which just measure light as it is, or sensors which measure polarization, sensors which measure in the direction of light. We have thermal sensors which measure heat, temperature, or we might be taking a whole thermal image. And you can write a whole, well, there are massive volumes of manuscripts on how different type of sensors there are. And there lies the problem. All the neural networks we are talking about is going to process the data coming out of sensors. The question then lies, how do we connect these two sensors? How much energy do we waste in connecting this? So you saw earlier Professor Bhaskaran's talk about optonic devices, but you have to transfer data from sensors going to these photonic devices. You would lose quite a lot of energy there. I mean, here is an example of how large number of sensors, but even if you go away from human beings. So these are arrays of sensors on a bridge. And this is a bridge in Athens, in Greece. It has a 2.25 kilometer suspension bridge with 300 sensors. So we're talking a bit older bridge, which has strain gauges to keep track of framework fatigue, motion sensors to look at what is happening to stay cables. Is there wind motion? Accelerometers to measure any impact on earthquakes. Those are the sensors on the bridge. And then what do? We have got data acquisition unit, one in each pier of the bridge, which are then send the data to the bridge site. So we have a local data processing service. Data also goes to the headquarters of the bridge company in Athens, which is constantly monitoring whether the bridge is good or not. And then it's also going to the structural monitoring division of the bridge builders in France, in Paris. So 3 places data is being collected, transferred, and then processed. So a huge amount of data bandwidth is being wasted with these sensors. Now, in general, let's keep on a bit general about sensors. I mean, most sensors from electrical engineering point of view would be measuring any electrical property, or will be transforming a physical property into an electrical property. So we generally measure things like pressure, displacement, temperature. And we transform these non-electrical quantities to electrical quantities, which could be change in resistance, inductance, capacitance, voltage, current. Or we might have transducers, which transform from one domain to another domain. So they take an input domain, say something like pressure, and convert it to strain, and we then measure the strain of these devices. And for the same quantity, I mean, just for measuring temperature, you could have different type of sensors. I mean, you have mercury sensors, you have thermocouples, and there are some sensors which actually measure more than one property. I mean, they would have a primary variable, they will convert to secondary variable. So from an interface designer, it becomes quite challenging as to, can you design an application, can you design a general purpose neural networks or a general purpose processor for all of these sensory systems, or should you go and design individual neural algorithms for each one of these? So this diversity of sensors, unlike the processing data where you know the data is in binary form and you just need to extract them, there is a big diversity of sensors which makes our life a bit difficult. Now, unfortunately or fortunately, brain actually doesn't do that. It doesn't follow this paradigm of sensor, then do some signal conditioning, do some ADC processing, and then do this. It actually does both together. It learns and it senses together with kind of one organ. Now, most neural network people would generally think of brain as just the part where you have got the processing part happening. That's a very interesting thing. The brain also keeps its sensors close to itself. Most highly sensitive sensors, so ear, nose, mouth, and eyes, they are more sensitive than the sensors which are distributed. I mean, we have a sensor even in our toe, the skin, but skin sensitivity is actually not as high as the sensitivity and selectivity of these sensors. So good sensors are kept quite close to the brain, first. Second, most of these sensors start doing early processing, and people working on imaging would know that eyes have got ganglion cells which start doing early processing. And we certainly, to the best of our understanding right now, we do not convert data into digital domain. We might be converting into frequency domain, but that's still an open question from biology point of view as to what do we do of this data. So the brain keeps the senses together, which means the neural networks which we are trying to design should also consider what type of sensors it should interact with, and should most possible, better still, be designed together with the sensing system itself. Now that should happen, but those are difficult to do. And in the next 20 minutes, I will show why it is difficult to do and why this is still a research challenge to do. So as an example, I will take camera sensors for 3 basic reasons. First, there is a long literature base on people designing cameras. Right in the early days of cameras, people were making neuromorphic images. I mean, the human eye does a very interesting thing with light. It adapts to the input intensity. So people were designing pixels which adapted to input intensity, and that's the Delbruck and Mead pixel. So there's a big literature base on neuromorphic images. And a lot of neural network work is also concentrated on visual classification or visual recognition. So most of and large number of these neural networks take visual sensory data. So image sensors are a good database to understand sensors and why it's difficult to integrate neural networks with them. And third, of course, the reason being I'm an image sensor person, I design cameras. Before we jump into this, just a quick summary of where we are with related to the natural image sensor or the natural image sensor with early processing. I mean, if you look at the human eye, it has got a fairly large image sensor which is curved, and then has got early processing right there, right next to the sensor itself before it sends data to optic nerve. So we have about 100 million pixels, and we transform that to 10,000 data points going to our brain. Connect that to what our one of the better image cameras we have. This is a Canon 5D. It's a bit older pixel, 50 megapixel, 860 millimeter square, front 2D imager. Is still not near what a digital, what our human eye does it for it. So with that as the background, let's go back to fundamental how we capture light. So we'll be moving very quickly on how we are capturing light. Essentially, we use the property of light falling on a metal or any conductor would lead to electrons being ejected. So if light has a certain energy, based on the work function of the metal, if light falls on it, if it leads to a generation of electrons in semiconductors, it will lead to a generation of electron-hole pairs. We measure these electrons or these photons, and that gives us a measurement of the light available. And we transform that into a pixel. Fortunately for us, the material used for making most circuits or most processing elements is silicon, whose optical sensitivity very nicely maps to that of the human eye. This is a spectral response of a typical silicon detector. It goes from about 400 to 900 nanometer of wavelength, which is also blue to red wavelength to which our human eye is sensitive. So we have got good base to start with. So it was easier for us to move from film-based technology to various pixel-based technology. And some of the earlier, those about who are a bit older might remember the charge-coupled devices, wherein we had created just a bank of capacitors where light falls on it, generates charge pairs, and then we transfer these charge pairs all the way towards the end and read them out as an image. Earlier in the days of silicon, we also had simple things. We could just have arrays of photodiodes. So there's a 2-dimensional array of photodiodes with a switch connected to each one of them, very much like your crossbar architecture of one resistance, one switch. You have row decoders, column multiplexers, light falls on the diode, generates a photocurrent, you read out that photocurrent, and you have got an imager. However, that's not a good thing. And the reason why it's not a good thing needs a bit of maths. And let's do the bit of maths first. So light falls on it. So if we take a light which is about the lambda of 600 nanometer, this thing. Its energy is generally 2.07 electron volt. Now, if I take a typical diode and see how many photons would be there, I would measure the current. The current comes out to be 6 femtoampere. This is a typical diode, which is 10 micron by 10 micron size. Now, if I had a system like this, where there's a 6 femtoampere being produced, and if that 6 femtoampere was being asked to charge the entire column capacitance line, this imager would be quite slow, particularly if you have a large number of pixels. If you have a megapixel, you would have roughly 1,000 rows and 1,000 columns. This 6 femtoampere would have to charge that long line running across 1,000 pixels, which is, it will be able to charge, but be a very, very slow imager. Our aim was at least to 20 or 30 frames per second to capture video. This is where CMOS process was good. Standard CMOS process, in which we design all other non-optical processors and material. The first good thing was it had diode, so we can make a pixel. But the diode has poor optical properties. Remember, CMOS process originally was never designed to make cameras. It was designed to make processors and memory. So no one cared about the parasitic diode which is available. But it had the promise. Transistors become smaller, which means you can have more pixels. It could provide lower power, lower cost, higher speed. And because we were making processing elements, processors and memory in CMOS processes, we could bring these two together. Even before neural networks, even before we had the vision that we could put a processor and optical sensor together, and we can have a AK and I. However, what happened was we ended up not doing that. And the reason why we ended up not doing that would become clear here. We cannot design just a diode array, as I just talked to you guys. So we need to do something more inside the pixel to buffer that very small amount of 6 femtoampere current. Which means our simple circuit, which had just a diode and a resistor and a switch, is not good enough for imaging fast-moving scenes or even moving typical video. So we ended up designing a pixel which is called an active pixel sensor, and you would see 3 transistor or 4 transistor implementations. So we start with a diode, light falls on the diode. We then have a reset switch. Rather than just continuously measuring the light, we convert the photocurrent falling in the pixel to a voltage by integrating that photocurrent on the diode capacitance. At the start of every frame, we reset the diode capacitance. The light falls on the diode. It discharges this photodiode node. And you can see here, so at the start of integration frame, we keep this M1 switch on. The reset voltage falls on the node N1, of course, with a drop of threshold voltage. Then we switch off the reset voltage. This reset transistor, light falls on the diode. It discharges this voltage, this capacitance, the N1 capacitance. If the low light is there, it discharges a bit low. If there's a high light, it discharges a bit high. We then have a source follower to buffer this voltage. So now our diode is not going to charge the whole column line. We have a source follower, and then we have a switch here to access this particular pixel. We provide a high current to the source follower, which means that the charging of the column lines can be a bit quicker. So that's the active pixel sensor. Now, this has got 3 transistors and a diode. The next thing we have to do is, well, our end customer wanted digital data. The output of these pixels is analog. It's an analog voltage. Not a good thing for most digital processing or storage. So we have to convert this data into digital. The question is, where do we do that? Do we do that at the end of entire array? So if we have a 2-dimensional array of pixels, do we put a very large and powerful ADC at the end? Which is a bit problematic if you have a large number of pixels. So if you have 10 megapixels and you want 30 frames per second, which means your ADC should be going at 300 megasamples per second, which A is a bit challenging, but B, an ADC going at 300 megasamples per second is also going to produce heat. This heat in turn is going to heat all my pixels and increase the leakage current of the diode. So From there to an ADC per column, and that's a good design, because then one ADC only has to convert data coming out of pixels in a column. Now I have drawn this, which looks like the ADC is quite small compared to the number of rows. But if you actually design a high performance ADC and you try to put one per column, if you just have a megapixel imager, you have got 1000 ADC. The length of this ADC sometimes becomes the same as the length of your imager which you have. So if you have, ADCs typically will capture, say if you take a 0.18 micron process, it will be about 300, 400 micrometer long. That's almost the same length as about 500 pixels. So ADCs are taking a large amount of area on the chip. Of course, there are people who have pushed and said, okay, you know what, let's put a small ADC per pixel and get very, very high speed readout from images. Certainly possible, but now you're putting loads of circuit inside a pixel. Now I'll tell you why this is not a good idea. The ADCs are generally large. You can't design ADC from small number of pixels. So this is just a typical ADC. It's a ramp-based ADC. And you see the column circuits are already having a large number of transistors. We're having about 50 odd transistors. When we design a pixel, our ambition is actually to have as large photodiode as possible. If you look at the layout, we want a large photodiode to capture as much light as we can, because at the end of the day, it's an imager. So you want large photodiode and small number of transistor or small area devoted to transistors, because that's not going to capture any light. If we could have a diode sitting on top of the pixel, that's perfectly fine. If we had 3D integration, that would have solved our problem. But as of now, we want to have diode take as large an area as possible. And second, our customer wants as many number of pixels as possible. So the total area of the pixel shrinks, because in the same format, earlier you were asking for 1 megapixel, now you're asking for 20 or 100 megapixels, which means the pixel area of each diode, each pixel is reducing. So we have smaller pixels, and in the smaller pixel, we need as much area as possible to diode, which in turn means we can't really put more transistors. Even the 3 transistors we are putting are already taking quite a lot of area. So either we do that, or we have small number of pixels, which again, our end customer won't be happy. So people have gone through multiple ways on how to increase the diode area. We have shared the neighboring transistors, 4 photodiodes sharing the readout electronics and that way increasing the diode area. So all these techniques have been tried. But this does not lead to large number of pixels in the large number of transistors in the diode, or large number of memristors in the diode to actually do any neural processing. What I've not discussed till now are the features like noise. It's an optical readout system. It actually leads to quite noisy output. Most cameras produce a noisy output. And for example, the first picture is the kind of picture we generally see of a real life image like this. It has got noise because of temporal activity, but more importantly, remember, we tried to make transistors as small as possible. Small transistors have got mismatch. We have got small transistors would have mismatch. So the temporal noise I started talking about, you'll have short noise like photon short noise and DC current short noise. But we are also having a charging and recharging process, which means every charging process leads to a KTC noise. So we would have a reset noise on the pixel. So that's the temporal noise. And then we know each transistor is different to another transistor. I try to make my transistors as small as possible in order to make diode as big as possible, which in turn leads to mismatch. And the mismatch would have a standard deviation of some form given by the process. So the smaller geometry processes with smaller geometry transistors will have higher mismatch. Resultantly, I will get quite a noisy system. Now we use, if we took the whole noise process, even if this such simple system with 3 transistors, I'm adding reset noise, I'm adding photon short and noise, I'm adding flicker and thermal noises at different parts. All the ADCs are giving me noises. So I get a very noisy image. Those who have done image sensors courses would know that we actually learn from the charge coupled devices, and we have a floating diffusion inside the pixel. So we actually store the reset value as well as the readout, as well as the integrated value after a certain time, and take the difference between these two to find out. If you take the difference between these two, you are going to remove all the additive noises. So all the fixed pattern noise due to additive offsets will be removed. And if you also store the reset noise at the beginning of integration, that noise during the course of integration should not change. So you'll also be getting rid of much of the thermally generated reset noises. So KTC noise will go down as well. So we do this thing already, and already this floating diffusion takes area inside the pixels. So we are having a lower and lower fill factor of these pixels, which we don't like as imager designer point of view. So that's the pixel part. On top of that, our end customer wants a color image. So now we have to make red, blue, and green filters because our silicon is actually non-photosensitive. It has got a response to spectrum, but by itself, it gives signal to all the parts of spectrum. So we end up putting color Bayer pattern on top, or any sort of filter pattern. There is a typical pattern which has got double the number of green compared to red and blue. And so essentially, we are having a quarter less number of red pixels and quarter less number of green pixels. And then we go and try to figure out at the green pixel value what might be red. And one simple thing is take the average of neighboring red. So what I'm saying is that just the acquisition of signal part is challenging, and then we have the color filter to make our life interesting further. Despite doing all this, the pixel is not ideal. It does not give very good response as the human eye does. We have treated the noise part. It's not very high dynamic range. I mean, if you look at outside, if it's sunny at the place where you are, normal cameras cannot take images of very bright light or very dull light. So we have to then find mechanism on how do we capture at least the whole information in the scene. A lot of techniques have been developed in past. The reason why it happens is if you have a very high light, this integrating capacitive node falls down to almost just about threshold voltage of M2, and we cannot read it out any further. So the pixel saturates. We get a bright patch wherever we have got bright intensity. Techniques to improve this have been developed. I mean, the techniques were first needed when we did nuclear testing many years ago, because we had very bright light and we needed to take picture of this very bright light with this. So people tried cameras who recorded the same image but with different integration time. And you can do that. Many digital cameras provide you HDR option where they do this kind of dual sampling. They record one image with long exposure, one image with short exposure, and then try to stitch the images. The problem of doing this is it leads to SNR jumps. You have got different signal to noise ratio and different integration time. Resultantly, you get a bit of bad image. It's not the best image. The other solution is actually to go back to neuromorphic imaging. Remember, the human eye doesn't take a linear image. It actually takes a logarithmic image. It converts the input light into log light as soon as the light is achieved. And this has been done quite a lot, wherein people have tried to convert the incoming light into a logarithmic voltage by passing the light through a subthreshold transistor, here M1 being the subthreshold transistor. But the challenge remains, the low light levels lead to low photocurrent, which means the pixel becomes slower. So even though we can record a large intensity of light, we do not record it at a very high speed. Something happened. Sorry, that was my phone's ringing for a change. So now that's all for classical imaging. We can capture this thing. Of late, there has been work on why can't we do event-driven imaging? Why do we need to record all the information which is there in the scene? Can we just, if I can see the video, and the video won't do the trick. So let me try to share my entire screen and then see if we can do the video there. Yeah, doesn't like it. So hopefully you can see my entire screen. And there, if you can see, there's a person walking into this frame of incidence. A person walks in. Now, in this scene, we don't really need to record all the information which is there. We could go down and cut down the information which we're recording in rest of the scene and just look for a motion to take place and just record in that region. Or we could, just keep on randomly sampling rest of the scene and find the moment a motion takes place, we could increase the resolution of that region. We can do such activity. We could also go back and, sorry for hopping through my slides. Could also go back and do some form of compressed sensing. There has been a lot of work on local and focal plane compression, which are in, if you take a large screen, just take some parts of the scene or randomly sample the scene and then reconstruct the scene. Doing all of these means you are going to do some processing. And the question then it raises, where do we do this processing? Be it neural processing or be it normal processing, where do we go and do it? We can do it in the pixel. It's possible. I mean, here is an example from 2014 of a large pixel which undertakes some processing. But the moment you start doing processing in the pixel, you would have many transistors in the pixel. The diode will become smaller. You would be doing bad imaging. And the other drawback of this is your imager then becomes application specific. It can measure the flow. It can identify if there's a cat in the scene or not, but that's all it can do. It cannot do anything else. From a sensor designer, you actually want to design sensors which are as general purpose as possible. I mean, cameras which can identify a cat won't have a very big market. The other thing which we can do is, another example of how we end up designing cameras with loads of transistors and hence not get very high region is single photon avalanche detectors. I mean, here we are trying to measure very, very small amount of light. So rather than measuring light just as a direct photon generating electron hole pair, we take the pixel into the avalanche region where one photon leads to a large number of electron hole pairs. For these circuits, we generally need a counter. We need a comparator. So as you can see, we have got about 50 odd transistors in one pixel. We can improve this by trying to have an analog counter or trying to have analog type digital comparators, buffer integrator type comparator. But it still leads to very small fill factor. Little wonder single photon images are not available in multi-megapixel imaging. You only get them in 10 and hundreds of thousands if you ever get them. So we can't do processing inside the pixel. Can we do processing on the chip? We could possibly. We could have a system where there's a camera part of the chip and then there's a neural network part of the chip. But you have to either take one of these two things. Either you're going to make smaller imager, which means poorer quality of light, or smaller neural network. You could do things in the package or board, or you can go up to 3D integration, and that might be a better way of extracting information out of a scene. The question also is, where do we do this neural processing? Should we do before digitization or after digitization? Before digitization will reduce the amount of power wasted in ADCs, but you have to do digitization at some point of time. Some point, even if you have an analog neural network, the data has to be converted to digital because all our transmission and reception capabilities, all our storage capabilities are digital. So where do we do the digitization? At the sensory node, before neural network, after neural network, are the questions still open to consider for all of us. Then comes the question of how do we do the processing? People who are designing neural networks would like to process on a pixel by pixel basis. You could, in principle, design have a 3D integration. You could have a chip bonded, wire bonded to your image sensor where data of each pixel is sent into a neural network. But if you talk to neural network designers and then tell them that my input data is 1,000 by 1,000 pixel, that's not considered a very good input data because then the neural network size will become very, very large. So people subsample the scene. So there's a bit of a conflict here. People who are designing cameras are putting more and more pixels Whereas the people who are designing neural networks want a small array, 64 by 64, 128 by 128. So it's a bit of a conflict. The two sides are going in two different directions. You could, in principle, go by block computation, hence reduce the computation requirement, but also reduce the computability. Somewhere in between lies the sweet spot. We need to either rethink how we design our sensors, how we design our image sensors, or rethink how we design the neural networks. And somewhere in between, we need to think an architecture of this kind, wherein you have your sensor which produces raw analog data, take it to an analog neural network, which are in the analog domain. Now, you'll not be able to make large-scale analog neural networks. That's most probably is not going to happen in immediate future. In long-term future, if we end up with multiple layers of neural networks, that's perfectly fine. But immediate designers will not have that ability. So we need to have a small neural network. Now, question is, why do we put that neural network? Does it do anything? It might help us interface with the sensor. It will help us do early analog processing, and then have a digital neural network. I've written this software-based embedded AI, so this could be a neural network in FPGA or a digital processor or in the cloud. And let these two neural networks talk to one another. So the digital neural network could give the training data to the analog neural network, or could also tell how the network configuration will happen. That might be the way to go forward when we're designing smaller analog neural networks sitting next to a sensor. It could be one layer of neural network or two layers of neural network, which in turn talks to a layer of digital neural networks. The research problem then is, how do we break large neural networks into an analog part and a digital part? What performance matrices we should be looking at? Because the analog neural network will not just be, will be low power, it'll be significantly lower power than digital ones, but it will also be low capacity. It will have lower abilities to undertake any processing. So we have to divide a neural network in a low capacity neural network and a high capacity, high volume neural network to go on the digital side. And this is where possibly we could design systems which are general purpose. So you could still have a general purpose sensor, general purpose imager, talking to a general purpose analog front-end neural network, which is no more just the amplifier system, which is more than an op-amp or an ADC. This in turn talks to a digital neural network, and these two communicate between. So a sweet spot somewhere in between these two, similar to what we have in sensors, wherein the front end these days most of the time just buffers the input data and transfers the input data to digital. One also has to think about, if we transform the analog to digital here, what is the cost of digitization? Are we going to compress the input data to a smaller data set? If it does, I mean, right now I'm showing a neural network which is compressing the input data set. That would be perfectly fine, but would we actually be able to compress it, or with after a layer or two? I mean, if you're just having a CNN type neural networks, you would be most probably compressing. But depending upon which neural network, you might actually end up with larger number of points here, which then would require more ADCs. Or you might end up with large number of points here, but whose resolution is not the same resolution required for an imager. Typical imagers have 8-bit resolution, and the better quality imagers would push the resolution to 12 or 16-bit. So if we can cut down the resolution requirement, and even if we increase the area, then our overall power requirement of the neural network will fall down. So that, I believe, is the message from ICTIC, that this is the arena in which we should progress, rather than designing pure analog neural networks or pure digital neural. How to combine these two together with the sensory output should be the progress, would be the key question in future. Ideally speaking, if you want to increase the sensory data output, we have to merge the sensor and signal conditioning more than the way we are doing currently. We have to start early processing and possibly have more than one sensor together. And the signal conditioning should interface more than one sensor. It could be more than one image sensor, or it could be more than one different type of sensors, very much like the human brain does. It could be ears, eyes, nose, and so on and so forth. Thank you very much for giving attention to the talk, and have a good day. If you have any question, I'll be happy to take at this time.
Okay, so the first question comes is impact of aging and variability in case of sensors. What about the impact?
Now, that's a very good question. The answer is we don't know. The reason why we don't know is most of the widely adopted sensors are actually fairly new. The sensors, most of us end customers actually change our sensors very frequently. I mean, you change your mobile phone at a much higher pace than mobile phones are being manufactured. So we do not have long-term data of what would happen. Of course, one can simulate them. We can simulate pixels with high frequency performance. There are people looking at that, and then in due course of time, because we have a large number of pixels, what would happen is few pixels will die down. So, and one can have software system to, I mean, unlike standard processing system where there's one process is the bottleneck, we have a large number of pixels. So even if 10% of the pixels die down, we can compensate for it by nearest neighbor processing. The place where this is becoming more important are images which have been put on things like traffic system. You do not want to change them every 3-4 years. And this is where one has to learn very rapidly as to how we live with the aging of these pixels. But in general, digital sensors are very new for aging to affect them. And we are still, and they cost quite low. That's another problem. The cost is so low that people are happy to change rather than live with a sensor. The solution might be coming from the environmental lobby, where keeping on constantly changing the sensor is environmentally unfriendly. So we need to think about long life sensors.
Yeah, there is no question there, but I'll ask one question from my side. So since the imaging side, like you have more and more pixels like stacking up like each day, and it's ever increasing, it's always increasing. When we think about mixing up such a sensor to an analog neural network, you're still looking at like a large input that goes into your analog array. So what do you think about it? Is it really required to do that, or do we go back and reduce the size of the imager and do the generation at a later stage?
I mean, I generally ask my end customers, how many pixels do you need? And the answer almost always is as many as we can get, without knowing why we are looking for as many as we can get. I mean, the good old metric of a good image sensor was 3.2 megapixel, because the number you would like to have in order to print a good quality image. If you are printing a postcard size image, you need 3.2 megapixel. If you're printing an A4 size image, you're looking at 5 megapixel image. Yes, they give digital zoom. Yes, they allow you to have other functionality, but in a classic imaging perspective, you don't need that many number of pixels. So I guess when we are designing an image sensor with neural network, we have to cut down the number of pixels first. And B, once you have integrated an analog neural network, you have only made it an application-specific imager. You have designed your neural network to do something specific. The imager then doesn't need to become a general purpose imager if you're integrating it. I mean, for example, if you're doing a number detection, if you're running it on an MNIST database, 64 by 64 is enough for a number of applications. Then you could possibly imagine that having just a small number of pixels. The other thing which might come, which we should consider, I know me and you have talked about it, we never did anything about it, was the architecture of imagers comes because we were trying to design and pick a sensor which gives something which can be displayed on a TV screen, a two-dimensional architecture. The human eye doesn't do two-dimensional, it actually does a curvature architecture, right? We have a curved field of view. So we are designing this two-dimensional field of view, possibly, and this is where the neural networks and pixels could come together. If you want to put a neural network next to a pixel, you have a tiny pixel, a big neural network, but you have pixels of different dimensions spread around the whole focal view. And then you can possibly design and make them work together, this thing. So yes, we have to cut down the number of pixels. We also have to cut down the architecture. And this is a question for neural networks developers. If you don't have a 64 by 64 uniformly sampled grid of image, can you make a neural network to work with it?
Yeah, so basically we have to then look at the architecture as well.
Yes. So till now, people are looking at architecture of neural network. We have to think about architectures of the sensor itself.
So another question is, I think, if the surrounding is moving fast, can the image sensor capture with good quality?
Depends upon how fast it is moving. So
Yeah.
30 frames per second is the standard video frame, which most sensors can do. People do design very high speed moving scenes. There are cameras which can do 1,000 frames or 50,000 frames per second. A number of these cameras have been designed for defense applications. So they are generally export controlled from one country to another. And you can think of people working in defense are interested in how fast a bullet is moving or how fast a rocket is moving. So those cameras are generally restricted to certain countries. So yes, there are also biochemical application cameras where people are looking at very high speed chemical reactions. And actually me and Alex wrote a project to design a very high speed camera in India, which fortunately didn't go through, but that is an ambition for us as well. So yes, high speed scenes can be captured. One depends upon what you mean by high speed.
Yeah. One more question. Could we think to compensate or select sensor data with processing like brain does with images or sound?
That is a very good question. There are two aspects to that. One is what does the brain do to images? It extracts information out of it, but does it actually deal with noisy data, or do the sensors produce nice data going to the brain? And then brain has got nice data to play with. Like in our processing system, we actually produce noise-free data, give it to a processor to extract information. And I was talking yesterday in the panel that if you get drunk, you see very noisy images. So chances are high, our sensors, ears, eyes, and nose, actually they produce noisy data and the brain extracts information out of it. What the brain also does very nicely, it only extracts information it wants to extract. It does not extract all the information. So there is a cortical prediction theory that when you come to a room, and so you walk into your office and you see a scene which was exactly the way you left your office. There was chair, there's table. Your brain records the image but doesn't do any processing. It just ignores the whole image. It's only when you have got another chair, another person sitting there, just the brain starts complaining, something is different. So the brain does very selective processing. Now, problem with us is we are actually trying to design general purpose imager and general purpose processor. So yes, we could design systems which could be able to process, but then we have to figure out what exactly we want to extract.
Yeah, another question, like what are the challenges that we are looking at if we are to implement like a neural network on the same chip as the image sensor?
Oh gosh, where to start? First is the imager. Either we're trying to make a neural network on the same chip, or we are trying to make neural network with the pixel. Neural networks themselves are fairly large. They can be very large depending on, so we need to cut down the size of neural network, and maybe we need to be less ambitious about what a neural network can do. B, as we talked about, we also need to be less ambitious on size of the pixel which we are going to deal with, the size of the image sensor which we are going to deal with. So we need to reduce the ambition in both the domain and then design a system together. Challenges from pure neural network point of view, if you're doing transfer learning, if you're learning in a GPU and transferring the information to a sensory system, probably it will be easier to design. However, if you're going to design in a memristor or a new type of memory-based system, have an optical base to design an optical imaging system, and then deposit a hafnium oxide on top of that, that is not in the immediate line of sight. This is a very good area of doing research, but from commercial system, I guess we will still be looking at two-chip solution in the immediate future. Possibly, we might have to look at how do these two chips talk to one another? Can we have better system of communication between the two? And that would be something to explore.
Yeah, another question, is cutting down the pixel lead to more pre-processing requirement before putting input into neural network, especially for object recognition?
I would like to say that neural network does the processing. So one would imagine that the pre-processing requirement, so pre-processing depends. If you're just buffering the pixel, then no. If you're just making it less noisy, no. But if you are asking the neural network to identify edges, one should think that the neural network would also be trained to look with, to deal with smaller number of pixels. Most neural networks which are being designed are designed for smaller number of pixels anyway, though smaller but larger area pixel. People talk about 128 by 1, they're not looking at 128 by 128 1 micron pixel. They're looking at large size pixel which has got a larger field of view. So yes, at one hand we can cut down the number of pixels, but then the field of view increase will mean the size of the imager will remain the same. So most probably it will not lead to more pre-processing requirement. Your neural network should be able to capable to deal with that pre-processing requirement. Of course, I'm passing the bulk over to neural network community, but that's fine for sensors people.
Yeah, something like super resolution and other things could.
Yes, could be achieved.
Okay, I think that's it. Thank you, Bhaskar. I think we'll move to the
Thanks,
next.
Alex. Being the host, we can't thank one another, but you're very welcome.
So anyway, so Abu, are you there?
Hi, Alex. Can you hear me?
Yeah, sure. You could try out to share your presentation.
Sure.